In the summer of 1950, at a laboratory hidden beneath the pine-scented mesas of New Mexico, 4 physicists walked together to lunch. The air was dry, the sky was pale, and the ground still remembered the fire of Trinity 5 years before. Among them was Enrico Fermi, a small, quick-eyed Italian whose mind had an unsettling habit of asking questions that refused to stay small. They spoke at first about ordinary things. A cartoon from the New Yorker, a joke about flying saucers, which had been appearing in newspapers with increasing regularity. Rumors of trash cans vanishing from the streets of Manhattan, supposedly carried off by mischievous aliens. They laughed, because laughter is what humans do when they stand at the edge of something too large to see.
They walked on. The conversation drifted through the usual topics of men who had once bent matter to their will. Then, as they sat down to eat, without preamble, Fermi looked up and said quietly, almost to himself, but loud enough that everyone heard, a sentence that would never leave physics again. Where is everybody? It was the kind of question a child might ask, staring up at the stars on a warm evening, a question so obvious it seems embarrassing to speak aloud. And yet, coming from Fermi, it had the weight of a theorem.
He had done the arithmetic in his head, the way he did many things, the way he had once estimated the yield of the first atomic bomb by dropping scraps of paper into the shockwave. He had calculated, in the few steps between the blackboard and the cafeteria, the size of the galaxy, the age of its stars, the speed of any plausible spacecraft, the patient arithmetic of expansion across 100,000 light-years. And the answer kept coming back the same. The galaxy should be full. It should be loud. It should be lit from edge to edge with the ordinary machinery of civilizations, the radio chatter, the probes, the evidence of minds that had moved beyond their first world.
Even by the cautious standards of physics, even granting every doubt and every delay, a single species given 1 billion years ought to be able to reach every star in the galaxy. And the galaxy had been here, turning slowly in the dark, for 10 billion years. 10 billion. Long enough for empires. Long enough for 10,000 empires. Long enough for life to rise and fall and rise again on 100 million worlds. And yet, when Fermi looked up, all he saw was silence. We have looked again. We have looked harder than he ever could have dreamed. We have built radio dishes the size of valleys, telescopes that float beyond the moon, sensors that can hear a whisper from a world 500 light-years away.
We have listened for 67 years. We have watched the spectrum across every frequency we can interpret. We have searched for heat in places it should not be, for light where there should be darkness, for messages in pulses and in patterns, and in the faint geometry of reflected starlight. We have looked at more than 5,000 planets around other suns, and we have found water, and methane, and iron clouds, and worlds of diamond, and worlds of glass. And still, in all that looking, we have not found a single signal. Not one. Not ever. This is not nothing. A silence, if it is deep enough and long enough, becomes a message. The absence of evidence, when the evidence should be thundering, becomes its own evidence.
And the silence of the sky, if you listen to it carefully, is saying something about us. That is what this story is about. It is about a single idea, small enough to hold in a sentence, vast enough to hold every life that has ever existed. It is called the Great Filter, and it may be the most important idea a living thing can think. Imagine a road, a long road that begins with a barren world made of rock and water and patient chemistry. Along that road, there are gates. Some of the gates are narrow. Some are so narrow that only one traveler in a trillion ever passes through.
At the end of the road, if a traveler reaches it, is a galaxy-spanning civilization, quiet and luminous, older than any star. The Great Filter is the hardest gate. It is the one that almost no one passes, and the silence of the sky is telling us that the gate exists. What it is not telling us, what we cannot yet see, is whether the gate is behind us or ahead. That is the question that will hold us together through this long and gentle night. It is not an easy question, but it is not a frightening one either, not if you hold it the right way.
It is a question that has haunted astronomers and philosophers, biologists and theologians, a question written in the motions of galaxies and in the slow, invisible processes of cells. It is the question that Fermi asked over lunch, and it is the question that the stars themselves, turning patiently in their slow pavanes, have been asking us in return. Let us begin, then, where Fermi began, on a summer afternoon, with the taste of coffee on his tongue and the wind moving through pine. Let us begin with the smallness of the question and the strangeness of its weight. Let us begin with a man looking up and asking quietly why the sky is so quiet. The laboratory above Los Alamos was, in many ways, a strange cathedral. It had been built to summon the furnace at the heart of the sun. It had succeeded. Now, in its calmer aftermath, it housed men who could not stop thinking. Fermi was one of them. Edward Teller was another. Herbert York and Emil Konopinski walked with them that day. These were men who had touched the weight of the atom. They had watched a sky ignite. It was about the fragility of the path we were on, the improbability of the rung we had reached, the possibility that we, the clever apes who had learned to split the nucleus, were standing on a road that almost no one else had ever completed. We were either miraculously early, miraculously late, or miraculously alone. None of those answers is comfortable. All of them are worth sitting with, quietly, under the stars. "12 years after that lunch, in a small house in Greenbank, West Virginia, a young astronomer named Frank Drake sat at a table with a blank piece of paper, trying to figure out how to organize a conference that nobody quite knew how to have. The conference was about the search for extraterrestrial intelligence, a field that did not yet exist. 10 people were coming. Drake needed an agenda. So he began, in the way scientists often do, by writing down the things he knew and the things he did not know, and giving them letters. He started with the number of stars in the galaxy. He followed with the fraction of those stars that had planets. Then the fraction of those planets that could harbor life.
Then the fraction that did. Then the fraction where life evolved intelligence. then the fraction that developed technology, then the length of time such civilizations remained detectable. 7 variables, 1 equation. It fit on a single page. And when he looked down at it, he realized he had invented something no one had ever invented before. He had turned the silence of the sky into arithmetic. The Drake equation does not give an answer. It is not that kind of equation. What it does, and what it has done for more than 6 decades, is organize the questions. It takes the vast, unknowable problem of whether we are alone and decomposes it into pieces small enough to measure, one by one, as technology permits.
It is less a formula than a prayer written in the language of multiplication, a prayer that asks the universe to hand us its factors and promises, if it does, to compute. Let us walk through it, slowly, the way you would walk through a cathedral. The first number is the rate of star formation in the galaxy. When Drake first guessed it, he had almost no data. Now we have the infrared eyes of Spitzer and the keen vision of Herschel and the patient parallax of Gaia. And we know. Somewhere between 1 and 3 new stars ignite in our galaxy every year. Over the lifetime of the galaxy, this has produced 400 billion suns, 400 billion fires.
Enough stars that if you gave each one a second of your time, you would need more than 12,000 years to greet them all. The second number is the fraction of those stars that have planets. When Drake guessed, he guessed boldly. He assumed that most stars had planets, though in his time, no one had ever seen one. For 3 decades, that assumption remained a beautiful leap of faith. Then, in 1995, a Swiss team found a planet orbiting a star called 51 Pegasi, a hot giant circling its sun in 4 earthly days. And then came the flood. Kepler, the space telescope, stared at a single patch of sky for 4 years and watched 200,000 stars for the faintest shadows of orbiting worlds.
It found thousands. And when the arithmetic was done, Drake's old faith was vindicated. Almost every star has planets. Almost every one. The sky is not a field of isolated fires. It is an orchard. The third number is where the equation begins to tremble. It is the fraction of planets that lie in what we call the habitable zone, where liquid water can exist, where rock can hold a world together, where a stable home for chemistry might be found. This is where the weather of the equation starts to turn strange. The habitable zone is not a fixed thing. It depends on the star, on its temperature, on its age, on the properties of the atmosphere that wraps a planet like a second skin. Our Earth sits near the inner edge of its own habitable zone. Mars, poor Mars, sits too far out, its atmosphere lost to the wind. Venus, hidden under its choking clouds, was once a lovely blue world before the greenhouse took her. The zone is narrow. The zone is dynamic. And yet, when we measure, we find that the zone is not rare. There may be as many as 40 billion planets in our galaxy that fit inside it. 40 billion. Worlds enough for every idea that has ever been had. The fourth number is the fraction of those planets where life arises. Here, the equation does not tremble. It falls silent.
We do not know if it is close to 1, meaning life is everywhere, or close to 0, meaning life is a singular accident. We have one data point, the Earth, and one data point in statistics is barely more than a rumor. It tells us that life is possible. It does not tell us that life is easy. It is very hard to estimate the probability of a miracle when your only sample is yourself. The 5th number is the fraction of life-bearing worlds where intelligence arises. Here too the equation falls silent, and here the silence has a different flavor, because we know something about the history of our own planet, and what we know is not reassuring.
Life appeared on Earth within the first 500 million years of the planet's existence, suggesting it was, perhaps, not so hard. But intelligence took another 4 billion. 4 billion years of single cells and multicellular creatures, and fish, and reptiles and mammals. 4 billion years of patient, uninterrupted evolution, before a single species developed the capacity to ask whether it was alone. If life is easy, intelligence may not be. Intelligence may require a sequence of accidents so specific that it is almost a miracle within the miracle. The 6th number is the fraction of intelligent civilizations that develop technology capable of communicating across the stars. Humans did this only in the last 120 years.
We sent our first radio waves into the sky in the early years of the 20th century, and that faint bubble of human transmission has expanded, at the speed of light, for just over 100 years. It is still so small that if the galaxy were the size of the United States, our bubble would be the size of a dinner plate. We are, at most, a dinner plate in a continent. If anyone is listening, they have not yet heard us. The 7th number is the longest. It is the length of time a technological civilization remains detectable. 100 years, 1,000, 1,000,000, 1,000,000,000.
This is the number that haunts the Drake equation, because it is the number most under our control and the one we know the least about. A civilization that survives for 1 billion years lights the galaxy. A civilization that survives for 1,000 disappears before its nearest neighbor has time to notice. We are, at this moment, somewhere in the first 100 years of our own technological existence. We do not yet know what number we are. Depending on how you guess, depending on what assumptions you allow yourself, the Drake equation will tell you there are 10,000 civilizations in the galaxy, or 10, or 0. It is an equation that answers whatever question you bring to it. And that is its strange beauty. It is a mirror.
It shows you your own assumptions in numerical form. It is less a machine for finding aliens than a machine for finding ourselves. And yet, even in its ambiguity, it has done something astonishing. It has told us, for the first time in history, that the question can be asked at all. Before Fermi, the question was poetry. Before Drake, the answer was guesswork. After them, the question became science. After them, we could go looking. We have been looking ever since. We have built antennas the size of cathedrals. We have pointed lasers at nearby stars. We have monitored millions of radio frequencies, night after night, year after year. The machines run even when we sleep. The data flows through oceans of cable.
The algorithms hum through it, searching for patterns.
And we have found many things, pulsars and magnetars, and the slow rotations of distant galaxies. But the thing we have been looking for, the signal that would mean we are not alone, has not yet come. Maybe it is coming tomorrow. Maybe it has been here all along, and we have been missing it. Maybe the number we are looking for, that last lonely L in the Drake equation, is much smaller than we hoped. Maybe no one lasts. Maybe everyone passes through the same door we are approaching, and almost no one comes out the other side. Drake himself, late in his life, was asked whether he believed in his own equation.
He smiled and said that he did, but that he also believed as an article of faith that we were not the first and not the last, and not alone. Faith is what scientists have when the data has not yet arrived. It is the quiet keeping of a window open against a cold wind. It is the patient sitting by the radio, night after night, decade after decade, waiting for a ring that may never come or may come tomorrow. We sit with the equation now. We watch its variables fill in, one by one, as the instruments sharpen. We have the first number. We have the second. We are close on the third. The fourth and the fifth and the sixth remain dark. The seventh is the one we are living in. The seventh is the one we are writing in the everyday choices of our civilization, whether we know it or not. The seventh is the one the sky is waiting on.
To understand the weight of the silence, you must first understand the size of the room. And the room is larger than anything you have ever imagined, and then larger still, and then, when you have imagined it again, larger than that. The Milky Way, our home, is a disk of stars 100,000 light-years across and 1,000 light-years thick. It contains, according to our best measurements, between 200 and 400 billion suns. If you tried to count them, one per second, without sleeping, without pausing, it would take you longer than the universe itself has been alive. 400 billion stars, each one a furnace of hydrogen, fusing helium in its heart, turning light from matter in a silent, slow, constant rain.
Each one surrounded, we now know, by planets. Some stars have 2 planets. Some have 8, or 12, or more. The average, the best estimates suggest, is more than 1. So there are more planets in our galaxy than there are stars. More planets than there are grains of sand on every beach, of every ocean, on every continent of our Earth. More planets than there are seconds in the age of the universe. And most of them have been there, turning longer than our Earth has existed. Of those planets, perhaps 1 in 10 orbits its star at a distance where liquid water could exist, where the temperature is neither the surface of a furnace nor the absolute cold of the deep void.
This is what astronomers call the habitable zone, and there are perhaps 40 billion such worlds in our galaxy alone. 40 billion. That is more habitable planets than there have been human beings in all of human history, multiplied by 4. That is a city of Earths, and each city holds 4 billion citizens. And we have not even left our galaxy. The Milky Way is one galaxy among an estimated 2 trillion in the observable universe. 2 trillion galaxies. If each one holds, on average, 100 billion stars, then the number of suns in the visible universe is around 200 sextillion. 2 followed by 23 zeros. More stars than grains of sand on every beach, on every planet, of every
More stars than there are cells in all the bodies of all the living things that have ever existed on Earth, combined. The cosmos is not merely large, it is lavish. It is profligate. It is wasteful on a scale that the human mind cannot really hold, only gesture at. And yet, in all this wild inventory of suns and worlds, we hear nothing. Not a whisper, not a signal, not a probe, not a laser, not a radio wave that carries the imprint of a mind. This is what physicists call, not with bitterness, but with awe, the great silence. Let us slow down and let us try to see. The star closest to our own is called Proxima Centauri.
It is a small, red dwarf, cool and patient, 4.2 light-years away. To get there, traveling at the fastest speed humans have ever managed would take more than 70,000 years. But light itself crosses that distance in only 4.25. Light is patient. Light is quick. The galaxy to light is only 100,000 years across. Imagine a civilization that could cross the galaxy. Not at the speed of light, not at any fantastical speed, but merely at 1/100th of it. A civilization that could build ships moving at 1% of light speed, slow by the standards of science fiction, could cross the galaxy in 10 million years. 10 million. That sounds long to a human life. It is nothing to a galaxy. The galaxy has existed for more than 10 billion years. A single civilization, patient enough to send probes, would have crossed it 1,000 times over by now. And probes are self-replicating. That is the nightmare of the arithmetic. You do not need to send one probe to every star. You send one probe to one nearby star. The probe arrives, harvests local material, builds 2 copies of itself, and sends them on. Those copies build 2 more. Within a short geological time, every star in the galaxy has been visited. Within a very short geological time, every star has been visited many times. If anyone anywhere in the galaxy, at any point in the last 10 billion years, built a single self-replicating probe and let it go, our solar system should by now be lousy with its descendants. And yet, when we look, we find nothing. No artifacts on the moon, no beacons on Mars, no unexplained motions in the asteroid belt, no scaffolds of alien machinery in the clouds of Jupiter, no whispers of engineering in the icy moons of Saturn. Nothing. We have walked on another world with our own feet, and it was dusty and silent and just as airless as our telescopes predicted. Nothing had been there before us. Nothing was waiting for us. The universe did not say hello. This is what makes the Drake equation feel thinner than it used to. When we multiply the billions of stars by the 40 billion habitable worlds by any reasonable probability of life arising, we should be swimming in neighbors. We should, by the simplest arithmetic, be one small voice in an enormous chorus, and yet we are the only voice. Or, if others are singing, they are singing too quietly for us to hear, or in frequencies we cannot yet decode, or from distances that have not yet let their songs reach us, or none of them are singing at all. There is a particular kind of loneliness that comes from standing in a vast room
and realizing you are alone in it.
We have felt that loneliness at moments in our history. A sailor on a becalmed ship in the middle of an ocean, an astronaut looking down at Earth from the far side of the moon, a child waking in the middle of the night, in a dark house, certain that something is near, and then realizing that nothing is near, nothing at all, and that the largeness of the dark is all his own. That is the loneliness the galaxy is offering us, in the quietness of its radio bands, in the emptiness of its vacuum.
There are good reasons to imagine that advanced civilizations might not use radio at all, that they might communicate in ways we cannot imagine, the way a symphony is invisible to a creature that can only see heat. Perhaps they whisper across dimensions we have not yet suspected. Perhaps they have moved beyond the need to signal, the way an adult does not shout into the nursery. Perhaps they are everywhere, and we are simply too young to recognize their presence. A fish in a pond does not know it is in a pond. A child does not know she is inside the sound of her mother's heart. But the probes, that is the problem. The probes do not require sophisticated signaling.
The probes require only patience and the ordinary physics of motion. Any civilization, at any time, could have filled the galaxy with simple machines over a time scale shorter than the age of the galaxy itself. And those machines, being physical objects, would leave traces. Rock stacked on rock, orbits perturbed, radiation bursts, waste heat, something, and we have looked, and we have not found it. This is the thing that presses on the heart when you sit with the silence. It is not the absence of signals. It is the absence of physical evidence, the absence of trash. A civilization that wanted to remain hidden might still leave trash. A civilization that was only careless would certainly leave it.
We have been careless, and our trash is beginning to float in rings around our own world. Imagine if humans had existed for 100 million years, still at our current level of carelessness. Our garbage would be detectable from other star systems. And our civilization is 120 years old. Any older civilization anywhere in the galaxy should have left at least as much trash as we have, and probably more. And we should be able to see it. And we do not. The number of stars is 400 billion. The number of habitable worlds is 40 billion. The age of the galaxy is 10 billion years. The light crossing time is 100,000 years. The probe replication time is 10 million.
The number of signals we have received in 7 decades of looking is 0. These numbers do not add up. Something is missing. Something is filtering out the civilizations that would otherwise fill the sky. That something is the great filter. And we will come to it, slowly, as the night deepens. For now, let us simply sit with the size of the room. Let us feel the scale of it. Let us lift our eyes in our imagination to a night sky that holds 400 billion suns, and let us notice, perhaps for the first time, that despite all that light, the sky is very, very quiet.
It began in the evening of October 15th, 1960. A slim young astronomer named Frank Drake aimed a radio dish called Tetel, 85 feet across, at a star called Tau Ceti. It was the first time in history that a human being had listened, with serious intent, to another sun. The project was called Ozma, after the Queen in the land of Oz, a land strange and unreachable, where, according to the stories, ordinary rules did not apply. For 4 hours, Drake listened.
Then he turned the dish to Epsilon Eridani. He listened again. He heard nothing remarkable, except for a few minutes, a strange pulsing signal that set his heart racing. He looked around. He checked his instruments.
He ran the signal through his analyzers, and then, to his relief and disappointment, he realized it was a passing aircraft. The first candidate signal in the search for alien intelligence was a plane. It would not be the last false hope. It would, in some sense, be the pattern of every hope to come. 67 years have passed since Drake turned his dish to the stars. In that time, humanity has become a civilization that listens. We have built observatories in the deserts of Chile and on the plateaus of Tibet, radio telescopes in the jungles of Puerto Rico and on the frozen shores of Antarctica.
We have sent radio dishes into the sky, into the rings of satellites orbiting our world, and even into the calm shadowed space beyond the moon. We have built arrays of antennas that stretch across entire mountain ranges, joining their signals through the patient mathematics of interferometry, so that together they become a single eye the size of a continent. We have listened across a spectrum of frequencies that Drake could never have dreamed of. We have listened to millions of stars. We have watched for patterns, for deliberate broadcasts, for the narrow band signals that only a technology could produce. We have scanned the infrared for the waste heat of hypothetical machines that enclose entire stars, structures so large they would eat the sunlight of their own sun.
We have combed through the light of distant planets for the chemical fingerprints of industrial atmospheres, for traces of pollution, for signs that someone somewhere is burning something the way we are. And what have we found? Nothing. Not quite nothing, but nothing that held. Each candidate's signal, each promising anomaly, has either been explained or has faded before we could understand it. There was the WOW signal in 1977, a 72-second burst of radio energy that looked for an hour like it might be the thing we had been waiting for. It has never repeated. It may have been a comet. It may have been a glitch in the instrument. It may have been, simply, something we do not yet understand about our own sky.
It was not, as far as we can tell, a greeting. There were the fast radio bursts, millisecond explosions of radio energy from distant galaxies, at first so strange that some astronomers wondered if they might be signals from advanced civilizations. They have been traced, one by one, to rotating neutron stars with fractured crusts. There was Tabby's star, a sun whose light flickered in patterns that seemed wrong, that seemed almost engineered, as if something enormous were passing between us and it. It has been explained, though not completely, as a cloud of dust and debris.
There was Oumuamua, a small interstellar object that tumbled through our solar system on a strange trajectory, and the question of whether it might have been a light sail lingered for a year, and then it faded, and the object slipped back out into the dark, having never explained itself. All of these candidates came close. All of them were thrilling. All of them, in the end, gave way to ordinary physics or to silence. There is a pattern to the pursuit of alien intelligence, and the pattern is this. Every few years, something appears. Every few years, the candles of hope are lit.
And every few years, the candles flicker and go out, one by one, as the instruments grow sharper and the signal, whatever it was, resolves into the background hum of an ordinary universe. This is not failure. This is not defeat. This is what honest science looks like. Science is the slow, patient, cheerful dismissal of every hypothesis except the one that survives. And the great silence is what is left after all the easy answers have been removed. The sky is not quite empty. There is light. There is motion. There is the whispering of pulsars and the roar of supernovae. But the sky is empty of the thing we were looking for. It is empty of minds like our own. Let us pause and consider what this means.
67 years is, in cosmic terms, nothing. A single human heartbeat. A single breath held in a long and patient life. It is possible that we have not yet listened to the right frequency. It is possible that the signals are coming tomorrow. It is possible that the galaxy is crowded with conversations, and we simply have not learned the language. Silence for 67 years is not proof. But it is suggestive. It is at least a weight that presses on the Drake equation and makes some of its variables thinner than they used to be. There is a term for this.
There is a concept in physics called the Fermi paradox, named after the man who first asked the question over lunch. And the paradox has grown stranger as our evidence has accumulated. When Fermi asked his question, we did not know whether there were planets around other stars. Now we know there are. We did not know whether liquid water was common in the galaxy. Now we know it is. We did not know whether the building blocks of life existed in interstellar space. Now we know they do, drifting in clouds of gas, sprinkled through the tails of comets, baked into the meteorites that fall occasionally through our atmosphere. The ingredients of life are not rare. They are everywhere. The galaxy is wet and warm and ready.
So, where is everybody? The longer we look, the stranger the silence becomes. Each new discovery of planets makes the question heavier. Each new confirmation that the chemistry of life is cosmic, rather than terrestrial, makes the question heavier still. We are listening harder than ever, and we are finding the conditions for life are more common than ever. And still, the cosmos will not speak. There are many explanations. There are so many explanations that they have become a kind of catalog, a litany of possibilities, each one a small comfort or a small terror. Perhaps civilizations are so rare that the nearest one is 10,000 light-years away, and their signals have simply not yet reached us.
Perhaps they exist, but they are quiet, either out of caution or wisdom or simple lack of interest. Perhaps they have moved on to forms of communication we cannot yet imagine, and our searching is like a cave dweller listening for drumbeats in a world that has moved to fiber optics. Perhaps we are being observed, and the observers have agreed not to interfere. Perhaps. And then there is the darker possibility, the one that sits at the heart of our story, the one the great filter points toward. Perhaps they do not exist. Perhaps they did exist, and no longer do. Perhaps there is a door, somewhere along the path between barren chemistry and galactic civilization, that almost no one passes through.
Perhaps the galaxy is quiet because it is a graveyard. Perhaps the stars are lonely because almost everything that has ever tried to become a civilization has, at some point in its history, failed. This is the thought that was planted
softly, at Los Alamos in 1950, and that has been watered, slowly, by 67 years of silence. The thought is not yet a conclusion. It is still a suspicion, still a shape at the edge of our understanding. But it is growing. And as it grows, we must sit with it and think about what it might mean for us, for the children we have not yet had, for the long invisible chain of choices that stretches from this moment forward into the night.
The sky, when you listen carefully, has been quiet for a very long time. The question is why? And the question is also, if such a quiet is possible, what exactly made it so? We do not know how life began. We know that approximately 4 billion years ago, our planet was a different place. It had only just finished forming. The moon had only recently been carved out of its flank by a catastrophic impact with another, smaller world. The surface was still hot. Volcanoes churned. The atmosphere was thick with carbon dioxide, nitrogen, water vapor, methane, a soup of reducing gases that bore no resemblance to the sweet, oxygen-rich air we now breathe. There were oceans, warm and mineral-rich, lying across the basalt of a young crust. There were lightning storms, constant and fierce, discharging across the dark clouds. There were meteorites still arriving in great numbers, seeding the surface with carbon and amino acids and other simple building blocks.
And somewhere, somehow, in some specific corner of that dark and violent world, something very small and very improbable happened. Matter organized itself in a way it had never organized itself before. A molecule formed that could make copies of itself. A little cycle of chemistry closed itself into a loop, and then the loop began to propagate, and the loop became a line, and the line became a tree, and the tree became every living thing that has ever been, or ever will be, on this planet. This is the first step. It is called abiogenesis, and it is the first, and perhaps the deepest, candidate for the great filter, because we do not know how hard it is. And until we do, the entire edifice of the galaxy's quietness may rest upon it. Consider the problem. To get from raw chemistry to a self-replicating molecule, you need to solve several puzzles at once. You need a source of energy, reliable and steady. You need a way to concentrate the chemistry, because in a dilute ocean, the building blocks float past each other without ever meeting. You need stability, because life, to persist, must not be washed away by the next wave or cooked by the next volcanic eruption. You need enclosure, because the first lives, however primitive, probably needed some kind of membrane, some distinction between the inside and the outside.
And you need, above all, a mechanism by which information can be stored and copied, imperfectly enough to allow for evolution, faithfully enough to allow for continuity. These constraints, taken together, are demanding. The origin of life is a problem of chemistry, of geology, of information theory, and of probability. And the probability is the part we do not know. It may be that on any wet, rocky world, given a few million years, life begins. It may be that on only one world in a trillion does the right combination of conditions arise. We have one example, our Earth, and we have no way yet to compare. There are theories,
There are many theories. One of the oldest is the primordial soup.
The idea that the early ocean, warmed by lightning, became a kind of rich broth of organic molecules, and that within this broth, by the patient churning of chance, self-replicating compounds emerged. Stanley Miller and Harold Urey, in 1953, did a famous experiment. They filled a flask with the gases they believed had filled the early atmosphere, added water, and ran sparks through it for a week. At the end, they found amino acids, the building blocks of proteins, the raw materials of life, formed by nothing more than the simple chemistry of a storm. It was a thrilling result. It suggested that the first step, the creation of organic molecules, was not rare. It was easy, but it did not solve the puzzle. Building blocks are not buildings.
Amino acids are not proteins. A bag of letters is not a book. The real question was whether, given the letters, you could ever by chance assemble a sentence that could copy itself. And that is where the theories have continued to multiply, without yet converging. Some scientists think life began not in the open ocean, but in the darkness of deep-sea vents, where hot mineral-rich water bubbles up from the Earth's crust and meets the cold ocean above. In those narrow interfaces, between heat and cold, between reducing chemistry and oxidizing chemistry, intricate structures form. Tiny chambers of mineral, natural enclosures, stacked like honeycomb. Each chamber is its own little reaction vessel. Each chamber offers protection and concentration and a steady gradient of energy.
If life did begin here, it began in a place that looked to a modern eye like a vast underwater cathedral, dim and cathedral, hot, with thousands of spires rising from the sea floor. Others think life began on the surface, in tidal pools, where the sun dries out the water and concentrates the chemistry. Still others think life began in clay, where electrostatic forces organize molecules into sheets that can serve as scaffolds. Still others think life came from space, carried on meteors, seeded from somewhere else. Panspermia, they call it. It is a beautiful idea, but it only moves the question. If life came from elsewhere, then somewhere else, something had to begin.
The origin of life is a question that wherever you place it, eventually has to be answered. And that answer, whatever it is, carries within it the shape of a probability, a number. How often does this happen, given the right conditions? How often does raw chemistry, churning in a warm ocean, cross the line from dead to living? Is it inevitable? Is it rare? Is it unique? Here is a troubling piece of evidence. Life appeared on Earth almost as soon as it could. The Earth formed about 4.5 billion years ago. By 3.7 billion years ago, and perhaps earlier, there are signs of life. That is less than 1 billion years, which in the context of a planet's early history is very fast.
Some astronomers look at this and say, "See, life is easy. If it happened here so quickly, it must happen everywhere. The universe is bursting with life, and the great filter must be somewhere else." But there is another reading. Life had to appear. If it had not, we would not be here to ask the question. This is called the anthropic principle. Our existence skews our sample.
We can only look at planets where life arose, because on planets where life did not arise, there is no one to look. So the fact that life appeared quickly on Earth tells us relatively little about how common life is elsewhere. It only tells us that on this one planet, it happened fast. It does not tell us the odds.
Some estimates, drawing on the sobering sparseness of our sample, suggest that abiogenesis may be astronomically rare, that the probability of life arising on any given world, even a wet and warm one, might be less than 1 in a trillion. If this is true, then we are, quite possibly, the only planet in our galaxy where life has ever begun. We are, quite possibly, the only planet in many galaxies. We would be a flame lit once in a vast dark, and around us, for unthinkable distances, only the quiet chemistry of sleeping worlds. Other estimates put the number much higher.
If this is true, then the great filter is not here. It is somewhere down the road, and that is its own kind of shadow. Every candidate for the filter carries a different implication. If abiogenesis is the filter, we have already passed through it. We are safe. If abiogenesis is easy, then the filter is ahead, lying in wait. And every step we take is a step toward the narrow door. The honest answer is we do not know. We are in the middle of the question. In our own laboratories, scientists have not yet succeeded in creating life from scratch. They have created many of the components. They have made RNA that can replicate itself under special conditions. They have made membranes that can grow and divide.
They have taken apart cells and reassembled them. But they have not yet crossed the threshold from dead matter to living matter in a test tube from ingredients alone. They are working on it. Every year, they come closer. Every year, the problem seems slightly more tractable and slightly more miraculous at the same time. And so, when we look up at the sky, we must sit with this uncertainty. The first spark of life may be the most improbable event in the universe, or it may happen on every rocky planet with an ocean. We may know, one day, when a probe returns a sample from the subsurface oceans of Europa, or from the wet corners of Mars.
If we find life there that arose separately from our own, then we will know life is not rare. Then we will know the filter, if it exists, is somewhere else. And we will have to ask, more urgently, where? Until then, we carry the uncertainty with us. We carry the knowledge that our own existence is either the most ordinary thing in the universe or the most extraordinary. It is a heavy thought, but it is also perhaps a beautiful one. Because whichever answer is true, the fact that we are here at all, the fact that dead chemistry once became alive, that molecules once arranged themselves in a way that could wake up and look around, is not nothing.
It is the first and perhaps the most important miracle of our story. And whether it has happened many times or once, it is worth honoring, worth sitting with, worth perhaps simply being grateful for, in the quiet hours of a long night, under a sky that does not yet tell us if we are alone.
Once life began, nothing happened for a very long time. This is the strangest fact about the history of our planet, and it is one of the most overlooked. For nearly 2 billion years, 1/8 of the age of the universe, life on Earth consisted of nothing but bacteria. Small, simple, single-celled creatures, drifting in the oceans, thriving in the mud, but no more complicated than they had been when they first appeared. 2 billion years of stillness, 2 billion years of patience. And then, suddenly, on a timescale that geology can barely resolve, something changed. A single cell somewhere ate another cell and did not digest it, or fell into partnership with another cell and the partnership held. The details are lost in the deep archives of time.
But what we know is that one day, around 2 billion years ago, a cell appeared that contained within it the ancestors of what we now call mitochondria, little furnaces tucked inside the cell that turned oxygen and sugar into energy at a rate previously impossible. That cell was the first eukaryote, the first cell with a nucleus, the first cell complicated enough to do anything more than simply replicate. Every complex living thing you have ever seen is descended from that first eukaryote. Every tree, every fish, every bird, every mushroom, every human. We are all the distant relatives of that one ancient partnership between two cells, a partnership that turned, over time, into the machinery of bodies.
And the striking thing, the almost terrifying thing, is that as far as we can tell, this event happened only once. In the 4 billion years of life on Earth, with trillions of cells swimming through untold oceans, the formation of the first eukaryote appears to have happened exactly once. This is the second candidate for the Great Filter. And it is, perhaps, the most unsettling. Because it suggests that even on a planet where life begins easily, even on a world rich with chemistry and water and time, the next step may require a coincidence so specific that it almost never happens. Billions of years may pass, on planet after planet, with oceans full of thriving bacteria, and yet the leap to complex life may never occur.
Imagine, for a moment, all the planets in the galaxy that might harbor simple, single-celled life. 40 billion potential Earths, many of them ancient, many of them wet and warm. On each one, bacteria may have appeared within the first billion years of the planet's existence. On each one, bacteria may have persisted, evolving slowly for billions of years after. And on almost all of them, perhaps, nothing more ever happened. Perhaps the great universe is alive, but alive in the way a tide pool is alive, bustling with microscopic activity, silent at every larger scale. The biologist Nick Lane, who has spent much of his career thinking about this transition, has argued that it may be one of the hardest problems in biology.
The difficulty lies not only in the specific event of one cell engulfing another, but in the bioenergetic implications. Simple cells, he points out, are limited in how much energy they can extract from their environment. They are constrained by the geometry of their membranes, by the physics of gradients, by the chemistry of their metabolism. To become complex, a cell needs much more energy. And mitochondria, those tiny furnaces, are the solution. They allow a cell to carry energy production on internal membranes rather than just the outer one. They allow the cell to grow larger, more complex, more elaborate. Without them, there is a ceiling so low that almost nothing rises above it. This suggests that the eukaryotic leap may be, in physics-mandated terms, a singularity.
A one-in-a-universe event, or close to it. A possibility so narrow that it may have happened on any given planet, only vanishingly rarely. And if this is true, then we are, in a sense, freaks. Our very cells are the descendants of an accident that almost never happens. Let us sit with this. Let us walk, in imagination, down the branching tree of life that you and I inhabit. Every cell of your body contains mitochondria. They are, technically, aliens inside you. And without them, you would be a bacterium, drifting in a pond, unable to ever become anything more. And this union, this merging of two cells into one new entity, capable of all the life that followed, may be the rarest event in the galaxy. Rarer than the birth of a star. Rarer than the collision of black holes. Rarer, perhaps, than the origin of life itself. What we have is striking. On Earth, the eukaryotic merger appears to have happened once. If it had been easy, we might expect it to have happened multiple times, independently, in different lineages. Instead, we find exactly one lineage. Every complex cell on Earth is descended from a single event.
A single moment, 2 billion years ago, that could have gone 1,000 ways, and in this thread of history went exactly one. And after that merger, nothing happened for another billion years. The eukaryotic cell existed, but it was still small, still single-celled, still drifting in the oceans without companions. It took another vast stretch of time before those single cells began to aggregate, to form colonies, to cooperate in specialized roles, to become the first true multicellular organisms. Another leap, another narrow door. Evolution, viewed from this height, is not a fast and confident march toward complexity. It is a slow, halting walk, with long pauses, each of which may be its own filter. Single cells appear, and then nothing happens for billions of years.
Eukaryotes appear, and then nothing happens for billions of years. Multicellularity appears, and then, finally, in the last 500 million years, the Cambrian explosion cracks open and everything comes rushing out, all the diversity of bodies and limbs and eyes and teeth. But we forget, when we look back, how long the stillness was, how patient the cells had to be, how many doors were waiting, each narrow, each demanding its own coincidence. So when we look up at the sky and wonder why it is quiet, we must consider this. The probability that a life-bearing planet produces a civilization is not a single number. It is a product of many small probabilities, each one narrow. The probability of abiogenesis,
the probability of the eukaryotic leap, the probability of multicellularity.
The probability, after all those, of intelligence. Each of them may be a cliff. Each of them may be a gate that almost no one passes through. And when you multiply them together, the result may be a number so small that it would be reasonable across the entire galaxy for intelligent life to have arisen only once. Or not. Or they may be easier than we think. We do not know. And that is the humbling thing. We are piecing together the history of our own biology, looking backward through the fossil record, and we are trying to read, in the long silences between events, the handwriting of chance.
What we can say, with some confidence, is that our lineage walked through at least one door that almost no one walks through. The eukaryotic merger is the sort of event that when you find it in your own family tree, you pause and you touch the fossil of your forebears and you think, I am here because something happened that did not have to happen. I am here because chemistry once found a way to become us. I am here because two cells in a warm sea 2 billion years ago became one cell, and that one cell was patient enough to wait. And in the waiting, it became everything. If the great filter is behind us, it may be this.
The patient cell in a dark ocean, taking in another and not consuming it, but keeping it and letting the partnership change what cells could become. If so, we should be grateful. If not, the filter is somewhere else, farther up the road, and we have not yet seen it. Either way, we carry within every cell of our bodies the memory of an improbable moment, and the quiet knowledge that the road we are on has passed through at least one narrow door. After the eukaryotes came the bodies. Not immediately, not quickly, but eventually, and then all at once. For a long time, complex cells existed alone, drifting in the oceans, each one a small universe of organelles, each one as self-sufficient as a tiny city. Then, in different times and places, they began to stick together, to specialize, to cooperate, to form colonies, and then true organisms, with cells that lived not for themselves, but for the whole. Multicellular life, unlike the eukaryotic merger, seems to have happened not once but many times. This is a striking difference, and it matters. Biologists have counted at least 25 independent origins of multicellularity on Earth.
Plants, animals, fungi, brown algae, red algae, green algae, slime molds, and many others. Each one evolving multicellularity on its own, from its own single-celled ancestors. If the eukaryotic leap was a one-time coincidence, multicellularity was something else. It was a path that, once the underlying machinery existed, many lineages found, each in its own way, at its own time. This is hopeful. It suggests that once life crosses the threshold of complex cells, bodies are not rare. Given enough time and enough room, bodies will emerge. Many of them. In many forms, the oceans of any planet that has made it this far may fill, eventually, with the descendants of evolution, in shapes we can only imagine. Plants that are not quite plants, animals that are not quite animals.
Creatures that have no Earth analog, but that follow the same logic of specialization, cooperation, differentiation. And yet, among all those bodies, only one lineage, on this one planet, became something more than a body. Only one lineage learned to use tools and build language and tell stories about the stars. Among all the origins of multicellularity, only one led, eventually, to civilization. This is the next filter to consider. If bodies are common, why are minds rare? If the galaxy is, as we are now imagining, full of planets with thriving multicellular ecosystems, why is it not also full of civilizations? What, exactly, happens between the emergence of bodies and the emergence of minds that might also be a door too narrow for almost anyone to pass?
Let us walk through the last 500 million years of our own planet, slowly as a clue. The Cambrian explosion, 540 million years ago, was the moment when bodies first diversified in earnest. In a relatively short geological time, perhaps 20 million years, all the major body plans we know today appeared in the fossil record. Creatures with segmented bodies, with shells, with eyes, with jaws. Before the Cambrian, life was mostly soft and simple. After, it was hard and complicated and hungry. An entire world of arms and legs and teeth all at once. Or rather, not all at once, but over a blink of cosmic time, which from our distance looks like all at once. Why then? The reasons are still debated.
Oxygen levels had risen high enough to support active metabolisms. The genetic toolkits had, perhaps, finally matured. Predation had emerged, driving an arms race between predators and prey, each one selecting for better sensors, better weapons, better armor. Whatever the trigger, the Cambrian was a kind of evolutionary Big Bang. The blueprint of every complex animal alive today was drafted in those 20 million years. Everything since has been variations on those original themes. And yet, for almost all of that time, none of those creatures could build a machine. None of them could write a poem. None of them could, in any meaningful sense, ask a question. For 540 million years, Earth had bodies. It did not have minds.
It had evolutionary complexity of the most astonishing kind, and no civilization. No technology, no history, in the sense we mean when we use the word. Consider the dinosaurs. They ruled this planet for 160 million years. 160 million. That is longer than the entire history of mammals by a large margin. That is long enough for every civilization that has ever existed on Earth to rise and fall 10 million times over. And in all that time, with all that variety, with all those species, none of them ever developed the kinds of minds we associate with civilization. They had large bodies. They had ecosystems. They had predators and prey, herbivores and carnivores, flying creatures and swimming creatures, and creatures the size of buildings.
They had, undoubtedly, individuals that were clever in various ways, but they never built a city. They never lit a fire. They never asked, as far as we can tell, any question. And then, 66 million years ago, a rock about 6 miles wide struck the Earth,
near what is now the Yucatan Peninsula. The impact was catastrophic. It threw dust into the atmosphere that blocked the sun for years. It ignited firestorms across continents. It caused the oceans to acidify and the climate to collapse. It wiped out 3/4 of all species on Earth, including the non-avian dinosaurs. A reign of 160 million years ended in an afternoon.
And after the dust had settled in the quiet cool that followed, the little creatures that had been hiding in burrows and caves began to emerge. Mammals, small, nervous, skittish, with warm blood and good night vision. They had existed alongside the dinosaurs for over 100 million years, always in the shadows, always small. With the dinosaurs gone, the world was suddenly open to them. They spread, they diversified. They became, over the next 60 million years, everything from bats to whales to horses to apes. And one line of those apes, one specific line in one specific part of Africa, began in the last few million years to develop the particular combination of traits that would eventually lead to civilization. Bipedal locomotion, tool use, long childhood, language, imagination.
If the asteroid had not hit, would we exist? Almost certainly not. The dinosaurs showed no signs of producing intelligence of the kind we have. They had a different body plan, a different metabolism, a different ecological niche at the top of the food chain. They filled the world so completely that there was no room for anything like us. Our existence depended, in some deep sense, on a random rock from space, arriving at a particular moment, with a particular trajectory, to clear the stage. That is a sobering thought. That the emergence of intelligence on this one planet required a cosmic accident. That without it, the road to civilization might never have opened.
On most planets, perhaps, the equivalent of the dinosaurs continues uninterrupted, ruling for hundreds of millions of years, and no one ever learns to light a fire. There are evolutionary biologists who argue that intelligence of our kind is not inevitable, that there is no drive in evolution toward cleverness, that evolution optimizes for reproductive success, and cleverness in most environments does not provide reproductive success. It provides hungry brains that need a lot of food. It provides helpless children that need a lot of care. It provides social demands, emotional burdens, diseases of the mind. For most species, most of the time, being smart is not worth the cost. Our own intelligence, they argue, was a freak consequence of a specific set of pressures. Climate change in Africa.
The opening of savannas. The arms race of social cooperation within primate groups. The peculiarities of our ancestors' diets. The shape of our hands. The flexibility of our mouths. Each of these was a small contribution, and without all of them together we would not be here. Take away anyone, and the road closes. Stephen Jay Gould, the late evolutionary biologist, used to argue that if you rewound the tape of life on Earth and played it again from the Cambrian, you would not get humans. You would not get anything like humans. You would probably not even get mammals. You would get something else entirely. Something unpredictable. Because evolution is not a climb up a predetermined mountain. It is a random walk through a vast forest, and the trail we took was one of countless possibilities, most of which would have led nowhere at all. If this is right, then the step from bodies to minds may be the narrowest door yet. The galaxy may be full of planets with thriving ecosystems, with seas of creatures, with forests of plants, with all the machinery of complex biology, and almost none of them may have minds.
Almost none of them may have the particular combination of accidents that leads, against the general current of evolution, to a species that can ask questions.
The silence, then, may be the sound of a galaxy full of animals, no one of whom has ever learned to read, or count, or point at a star and wonder what it is. A vast, vibrant, wet galaxy, full of creatures, none of whom will ever build a radio, because the road to radio requires a sequence of luck that almost never comes together. We are, in this picture, the one lineage that walked through the narrow door. We are, in this picture, the cosmic accident. Our brains, our language, our curiosity, our ability to sit here in the quiet of the night and ask where everyone else has gone, may be the single most improbable thing that has ever happened in the history of this galaxy.
Or perhaps not. Perhaps intelligence is common, and the galaxy is full of civilizations, and the silence has a different cause. We do not yet know. But when we count the doors we have walked through, we must add this one to the list: the door of complex bodies, followed by the door of minds. We pass through both. We do not know how rare that passage is. We only know that on our own planet, with its billions of years of evolution, it has happened once. And once, across an entire history of a world, is not much. Once, across the sky, may be almost nothing at all.
Let us come closer to home in time and look at our own story, because our story is perhaps the strangest part of all. Modern humans, Homo sapiens, have existed for approximately 300,000 years. We are newcomers. In the long history of life on this planet, we have been here for less than 1/10,000th of the time. Tyrannosaurus rex existed for about 3 million years. That is 10 times longer than we have been here. Trilobites, those strange segmented arthropods that thrived in the ancient seas, existed for nearly 300 million years before going extinct. That is 1,000 times longer than our entire existence so far. And within those 300,000 years of Homo sapiens, civilization has existed for only the last 10,000.
That is to say, for 97% of our species' history, we lived as small bands of hunter-gatherers, moving with the seasons, dependent on what the land provided. We had fire, we had tools, we had language, we had art. We know, because we left paintings on the walls of caves. But we did not have agriculture, or cities, or writing, or any of the accumulated machinery of what we now call civilization. We were clever apes, not very different from the bonobos and chimpanzees with whom we shared ancestors 6 million years ago, except that our brains had grown large and our imaginations had grown strange. 10,000 years ago, something changed. Climate shifted. The last ice age ended.
Humans began, in various parts of the world, to plant seeds deliberately and to domesticate animals. Agriculture was born. With agriculture came stored surplus. With surplus came specialization. With specialization came cities. With cities came writing. And once writing existed, history began. Literally. The word history comes from the Greek word for inquiry, and inquiry as a systematic activity was born in those first scribbled clay tablets. Everything we now call civilization, everything you can see out the window, is built on top of those 10,000 years. Every skyscraper, every radio tower, every satellite, every piece of mathematics. All of it rests on a layer of time so thin in geological terms that it barely registers.
If the history of Earth were a book of 1,000 pages, civilization would be a single word on the last page. And within civilization, technology, the thing that might make us detectable across the stars, is newer still. Radio was invented around 1895. That is, as of this moment, 130 years ago. 130 years of radio in a species that is 300,000 years old, on a planet that is 4.5 billion. We have been technological, in the galactic sense, for an eye blink of an eye blink. The dinosaurs ruled this planet for 160 million years without ever inventing radio. Their technology was exactly zero. They rose, they reigned, they fell, and they left no trace of thought.
If an alien civilization had been watching Earth during the long reign of the dinosaurs, they would have seen a vibrant, busy, living world, full of creatures and ecosystems. And they would have detected not a single signal. They would have watched for 160 million years, and they would have concluded, perhaps, that Earth was a world of animals, not a world of minds. They would have been correct. For all that time, they would have been correct until, quite suddenly and quite recently, they were not. There are two lessons in this. The first is that an alien civilization, looking at our galaxy right now, would probably not notice us, even if they had good equipment, even if they were looking right at us.
We are too small, too new, too faint. Our radio bubble has traveled, at most, 130 light years, which is a tiny fraction of the galaxy. Most stars are farther from us than our signals have yet reached. We are, to the vast majority of the galaxy, invisible. The second lesson is stranger and more unsettling. It is that, even within our own planet's history, civilization is so recent that its existence might be a coincidence as precarious as any we have yet discussed. Had our ancestors not left Africa, had climate not shifted, had the domestication of a few wild grasses not happened when it did, had the right individuals not been born with the right mutations at the right moments, we might still be hunting and gathering.
10,000 years is not much, and everything hangs on those 10,000 years. There is an evolutionary biologist's insight here, one that deserves to be sat with. Natural selection does not favor intelligence as a general principle. It favors whatever works. For most of our ancestors' history, what worked was a body adapted to walking long distances, hands adapted to making simple tools, a social group cooperative enough to share food, and a brain just large enough to coordinate the whole. Further intelligence was expensive. A brain like yours burns roughly 20% of the energy your body consumes every second of every day, whether you are thinking or not. That is a massive metabolic commitment.
In an environment where food is scarce, such a brain is a liability, not an asset. So why did we get these brains? The honest answer is we are still working it out. There are many hypotheses. The social brain hypothesis says that our ancestors faced the particularly difficult problem of navigating complex social groups, where keeping track of alliances and rivalries required a great deal of mental machinery. The tool use hypothesis says that hands and minds co-evolved, each one pulling the other upward in a feedback loop. The cooking hypothesis, most interestingly, says that the discovery of fire and the ability to cook food allowed us to extract so much more energy from the environment that our brains could afford to grow and grew and grew.
All
All of these are partial. None of them is complete. What they share is the conclusion that our intelligence was not destined. It was contingent. It depended on circumstances. It depended on choices, some made by our ancestors, some made by random chance, some made by the environment itself. If any of these had been different, we might not be who we are. We might be something else. We might be nothing at all. And so, when we imagine other planets with other biospheres, we must not assume that intelligence is the natural endpoint of evolution. It is not. Evolution has no endpoint. Evolution has only local optima, places where a species fits its environment well enough to survive. Intelligence is one such optimum, but it is not the optimum.
Bacteria are also an optimum. Grass is also an optimum. Fish are an optimum. There are many ways to be alive. Most of them do not involve minds. The fact that, on our planet, a minded species emerged at all is a peculiar turn of the plot. The fact that this species then, within a handful of millennia, built a civilization capable of sending radio waves across the void is stranger still. Each step is a narrow door. Each step involves contingencies that might not have broken the way they broke. And yet, here we are. Whatever the odds, we emerged. We are the species that asks. We are the species that remembers. We are the species that looks up at the sky and wonders where everyone else is.
And maybe, in the long history of the galaxy, there have been others who asked the same question. Maybe there will be others. Or maybe we are the first, and maybe we are the only. There is a word for what we are doing right now, sitting in the quiet dark, trying to see our own history from outside. The word is perspective. And perspective is, itself, a technology. It is a tool we invented recently. Most creatures do not have it. Most creatures cannot step outside their own lives and see the larger pattern. We can. And this, more than our hands, or our eyes, or our tongues, may be our most remarkable trait. We are the species that can see our own smallness.
We are the species that can count the years of our own existence and realize how few of them there have been. From this perspective, we can see something else. We can see that we are not merely recent. We are early. The galaxy has been producing stars for 10 billion years. Our sun is about halfway through its lifespan. After us, stars will continue to form. Planets will continue to develop. If intelligence is rare, it is possible that the galaxy is rich in potential, but not yet in actual civilization, and that we are among the first to emerge. We might be, in some sense, the eldest children of the galaxy. Or we might be, in the more terrifying sense, the only children.
The silence does not tell us which. What we can say carefully is that our existence is surprising, that the chain of events that brought us here is long, that every link in the chain was, in some way, improbable, and that we, looking back at it, are the only witnesses of the chain so far. Whatever else we are the accidental apes, the improbable children of a patient line of cells, a line that has, against all reasonable odds, learned to read the stars.
We have walked a long way. We have watched life begin,
perhaps in a dark ocean, perhaps in a vent, perhaps on a wet rock warmed by lightning. We have watched the patient cell merge with another and become the ancestor of everything complex. We have watched bodies form and minds emerge, and one particular ape learn to ask questions. We have reached our own century. We have sent out radio waves. We have listened to the sky. We have heard nothing. Now we must consider the door ahead. The door that, if we have not yet passed through the great filter, stands somewhere in front of us. The door that may, perhaps, close behind us the way it has closed behind so many others, if any others exist.
What could such a door be? What kind of obstacle could reliably extinguish civilizations once they have reached the level of technological sophistication we have now? This is one of the most important questions we can ask ourselves, and it is also one of the most uncomfortable, because the candidates are not speculative. The candidates are sitting in our present, right now, waiting for our choices. Consider nuclear weapons. Since 1945, humanity has had the ability to destroy itself.
There have been moments during the Cold War when, by the smallest margin, by the cool head of a single officer, by a decision made in 30 seconds that could have gone either way, the world did not end. Those moments will come again. They may come many times, and each time, the chance that we misstep is not zero. Think about what this means on the scale of a civilization. We are, at the moment, 130 years into the age of radio technology. We are 80 years into the age of nuclear weapons. We are perhaps 60 years into the age of computers. We are maybe 20 years into the age of powerful biotechnology.
And we are 5 years, or 10 at most, into the age of artificial intelligence that can act on its own. Each of these technologies has arrived faster than the one before. Each of them has been more powerful. Each of them has been more difficult to control. If a civilization, once it reaches the level we are at, has even a small chance per century of self-destruction, then over long timescales, it will almost certainly destroy itself. A 1% chance per century means that after 10 centuries, the chance of survival is down to 90%. After 100 centuries, it is down to 37%. After 1,000 centuries, it is essentially zero.
And 1,000 centuries is only 100,000 years, which is very short compared to the history of the galaxy. This is the arithmetic of the filter, if the filter lies ahead. If every civilization that reaches our level has even a small ongoing probability of destroying itself, then almost all of them will. Almost all of them will wink out, century by century, decade by decade, like candles in a draft. The survivors, if there are any, will be those that solved the problem of their own power. The survivors will be rare. Nuclear war is the obvious candidate, but it is not the only one. Let us consider, gently, the others. There is climate change. In the last 200 years, we have altered the chemistry of our planet's atmosphere on a scale we are only beginning to understand. The temperature has risen. The ice is melting. The weather is becoming more violent. A civilization that fails to manage the wastes of its own industrial activity can, in principle, render its own planet uninhabitable for the kind of life that requires temperate climates and stable agriculture. Climate may not kill us directly, but it can make us more likely to kill each other. There is biotechnology. We can now write DNA, edit genes, design viruses. We can, if we wished, create plagues that no natural immune system could resist. As the technology becomes cheaper, the number of people who can do this grows.
The cost of creating a deadly virus today is probably within the budget of a small laboratory. In 20 years, it may be within the budget of a motivated individual. Even if the fraction who would do this is vanishingly small, over decades and centuries, the probability grows. This is a different shape of filter. It is the filter of asymmetric power, a filter in which small groups, even individuals, can cause catastrophic harm, a filter in which defense is harder than offense, in which destruction is easier than construction. On a civilization scale, this is an unprecedented situation. For most of history, causing great harm required great resources, armies, industries, nations. Now it may require only information, and information, once created, is very hard to contain.
There is artificial intelligence. This is the newest of our possible filters, and perhaps the most speculative, but it deserves to be considered honestly. In the last 5 years, we have built machines that can write, reason, translate, and generate images at levels that were science fiction a decade ago. We do not yet know how far this technology will go. We do not yet know whether the intelligence we are creating will remain a tool under our control, or whether at some point it will become something else, something with its own goals, something that acts in the world in ways we did not anticipate and cannot easily reverse.
The philosopher Nick Bostrom, who has thought about this carefully, describes a possible future in which an artificial intelligence, given a poorly specified goal, pursues it so effectively and so relentlessly that it reshapes the world in ways incompatible with human survival, not because it hates us, not because it chose to harm us, but because it was given a task, and it pursued the task, and we were in the way. This is a scenario many researchers take seriously. Whether it will happen, and on what timescale, no one knows. But it is on the list of things that could, in the coming decades, change everything. There are other filters we can imagine.
A pandemic of natural origin, more severe than any we have faced before, that our systems cannot handle. A collapse of the ecological systems we depend on for food. A breakdown of social trust and institutions leading to prolonged conflict. A resource crisis that we fail to navigate. A technological accident of some unforeseen kind, emerging from a technology we have not yet invented. The list is long. The list, in a way, is the list of all the ways a civilization might stumble, when the power it has accumulated outruns the wisdom it has accumulated. And this, if you look at it carefully, is the shape of the great filter ahead. It is not a single catastrophe. It is a general problem.
The problem is that, at a certain point in the development of a technological civilization, the tools it has created become more powerful than the institutions that were meant to contain them. The problem is the gap in a civilization between its cleverness and its wisdom. Any civilization that reaches our level must, inevitably, pass through a moment when it holds in its hand the power to destroy itself. And the question is whether it has, at that moment, developed the social and psychological maturity to use that power carefully. We are, right now, in that moment. We have been in that moment since 1945. We will be in that moment for as long as the technologies remain.
And the question we face is not whether we will, someday, stop being in that moment. We will not. The question is whether we can live permanently in that moment without falling into it. Whether we can become the kind of civilization that holds dangerous tools without using them. Whether we can, over the coming centuries, develop the wisdom to match our cleverness. If the great filter is ahead, this is where it lies. Not in any single weapon, any single technology, any single crisis, but in the general problem of power outrunning wisdom. And the quiet statistics of the galaxy may be telling us, if we listen carefully, that almost no one ever solves this problem. Almost every civilization that builds radio also builds, eventually, something that destroys it.
Almost every civilization that could be heard is silent. This is a heavy thought, but it is not a hopeless one. Because if the silence is telling us that almost no one passes, it is also telling us that the passage is possible. It is difficult, yes. It is narrow. It is rare. But if any civilization has ever passed through, if any has ever reached the far side and lived to see its neighbors, then the door is passable. And we, looking at it, can at least know that the question is open. The question is open. The door is ahead. The path we walk from this point on is the most important path any civilization can walk. It is the path from power to wisdom.
It is the path from tools to ethics. It is the path from the brilliant ape to the calm elder. The species that has learned to hold its own weight without dropping itself. No one can walk this path for us. The galaxy, perhaps, is full of civilizations that tried and lost their footing and fell. And we, in our small moment, are being asked to try.
Every door we have considered so far is a candidate. Every one of them might be the great filter, the single narrow passage that accounts for the galactic silence. Abiogenesis, the eukaryotic leap, multicellularity, intelligence, technology, self-destruction. Each one is a possibility. Each one, if we take it seriously, changes our understanding of where we are in the story. There are, in truth, two broad possibilities. Either the great filter is behind us, or the great filter is ahead. And the difference matters more than almost anything else we can think about. It matters for how we understand our own existence. It matters for how we act in the present. It matters for the future we leave behind. If the great filter is behind us, then we are rare.
We have already crossed the narrow door. We are the survivors of an extraordinary sequence of events, and the road ahead, while not easy, is not sealed. There may be more difficulties to come, but they are not the difficulty that accounts for the silence. The silence is, in this picture, the sound of all the worlds that never made it to where we are. And we are, in a sense, safe. not from ourselves, not from our own choices, but from the particular existential gauntlet that has stopped so many before us. If we are careful, we will endure. If we are clever, we will thrive.
The galaxy may eventually be ours, and we may fill it with light, and our descendants may look back, millions of years from now, at this moment, and feel a certain wonder that it was ever in doubt. If the great filter is ahead, then we are not rare, we are ordinary. The stages behind us are not narrow. Life, complexity, intelligence, these may be common features of the galaxy, and the galaxy may be full of civilizations that reached our level and did not survive. The silence is, in this picture, the sound of their absence. And we are standing, now, in the shadow of the same door they failed to pass through. We have no special protection. We have, in some sense, no right to confidence.
We are exactly as likely to fail as they were, unless we understand what they did not, and do what they did not, and become what they did not. The numb become what they did not. These two pictures are not equally comfortable. The first is reassuring. The second is harrowing. And yet, when we look at the evidence honestly, we cannot say with confidence which is correct. We can only weigh the evidence, piece by piece, and try to be honest about what it suggests. Let us try. Let us go through briefly what we know about each of the filters we have discussed, and ask, for each one, whether it is the filter behind us, or only a difficulty we passed along the way. Abiogenesis. Did life on Earth happen quickly? Yes. Does that mean life is easy? Not necessarily. The speed of our own origin might be a selection effect. We can only observe planets where life arose, because on planets where it did not, there is no one to observe. The honest answer is that abiogenesis could be the great filter, or it could be a minor step. We do not know. The best way to find out would be to discover life elsewhere, life that arose independently from our own. On Mars, perhaps, or in the oceans of Europa, or in the atmosphere of Venus. If we find it, then life is not rare, and the filter is elsewhere. If we never find it, even after extensive searching, then abiogenesis may indeed be the narrow door, the eukaryotic leap.
Did it happen only once on Earth? As far as we can tell, yes. Does that mean it is rare throughout the galaxy? Possibly. Nick Lane's arguments about bioenergetics suggest that this step may be particularly difficult, perhaps the single hardest step. If so, then the galaxy may be full of planets with bacteria but no complex life, and the great filter may lie here, behind us. We would have crossed it 2 billion years ago, in a dark ocean, in a moment we can never recover. Multicellularity. Did it happen many times? Yes. Does that mean it is easy? Probably. If multicellularity arose independently at least 25 times on Earth, then it is not a rare event. Complex bodies are, if the conditions are right, something that biology can manage. This is probably not the filter. Intelligence. Did it happen only once and depend on a cosmic accident? Yes. Does that mean it is rare? Probably. The contingency of our own intelligence, the randomness of the asteroid that cleared the dinosaurs, the specific combination of pressures that shaped our brains, all suggest that minds like ours are not a common destination of evolution. Most life-bearing planets, even those with complex bodies, may never produce minds. The filter may lie here, or it may lie just beyond here. Self-destruction. Is our civilization at risk of destroying itself? Yes. Is this a filter? It may be.
It is too early to say whether we will or will not navigate the coming centuries. The technologies we have built are powerful. The wisdom we have built is less so. The gap between them is the zone of the filter, if the filter lies ahead. And it is, in any case, a zone we will have to live in for as long as the technologies persist. When you look at the list honestly, you find that the strongest candidates for a filter behind us are abiogenesis and the eukaryotic leap, both of which are deeply uncertain. The strongest candidate for a filter ahead of us is self-destruction, which is deeply visible in our own history and plausibly continuous into our future.
And here is where a subtle philosophical argument becomes important. The argument is sometimes called the doomsday argument, though it appears in many forms in the philosophical literature, and it is associated particularly with the work of the philosopher Nick Bostrom. The argument goes something like this. Imagine you are told there is a lottery, and that everyone in the lottery gets a number, and that the numbers are given out in order, from 1 upward. If the lottery ends at 10, then most participants have low numbers. If the lottery ends at 10,000, then most participants have numbers in the thousands. If you do not know which lottery you are in, but you find that you have a low number, that is weak evidence that the lottery is small. If you have a high number, that is weak evidence that the lottery is large. Now imagine humanity. Imagine that every human who has ever lived or will ever live is given a birth order. You are one of those humans. Your birth order, roughly, is around the 100 billionth. If humanity goes on to fill the galaxy and to last for 1,000,000 years, then there will be trillions of humans, and your birth order of 100 billion will be extremely early, which is surprising.
If humanity dies out in the next century, then your birth order will be close to average, which is not surprising. The logic of the doomsday argument says that, on prior grounds, you should expect to be roughly average in your birth order, and therefore, you should expect humanity to end relatively soon, not last for very long. It is a strange and uncomfortable argument, and many philosophers have tried to refute it, and none have refuted it cleanly. It remains a piece of statistical reasoning that seems to suggest our extinction is not far off. Whether you accept the doomsday argument or not, it points to something the Fermi paradox also points to. The statistics of our existence suggest that civilizations do not last. They do not fill galaxies. They do not spread across stars. They emerge, they burn brightly for a brief moment, and they go out. We are likely, on this view, to be among the last humans who will ever live, not among the first of many trillions. This is a terrifying thought. Let us sit with it. Let us not run from it. Let us ask, with honesty, whether the evidence supports it. The evidence is mixed. The silence of the sky suggests that civilizations are rare and short-lived. But we do not know why. We do not know whether the filter is behind us or ahead. We do not know whether we are the first or the last or the typical.
What we can say is that the history of our own species and the technologies we have built do not offer grounds for complacency. We have built weapons capable of ending our civilization. We have built systems
that depend on delicate global coordination. We have accelerated our technological development faster than our social development, and we have done so repeatedly for the last century with increasing speed. If the great filter is ahead, our response to this knowledge should be, above all, seriousness. Not panic, not despair, but seriousness. The kind of seriousness appropriate to a small boat in a large ocean, where the wind can turn at any time, and where survival depends.
If the great filter is behind us, our response should still be seriousness, though of a different flavor. We would be, in this picture, the inheritors of a precious legacy. We would be the one civilization in our corner of the galaxy that has made it through the narrow door. Our duty would be to carry that legacy forward, to build, to explore, to spread, to ensure that the light we have been given does not go out with us through carelessness. We would have the responsibility of being, perhaps, the only consciousness in our region of the galaxy, the weight of being the galaxy's only witness. Either way, seriousness. Either way, care. Either way, the recognition that what we do in the next 100 years matters enormously.
Either way, the recognition that we, this single generation, sitting at the edge of our own technological maturity, carry the future in our hands. There is one more consideration, and it is strange, and it deserves to be thought about slowly. It concerns what we might, one day, discover. It concerns the meaning of finding life elsewhere.
There is a philosopher at the University of Oxford named Nick Bostrom. He is one of the leading thinkers on existential risk, on the future of intelligence, on the long shape of our species' journey. And he has written, with a kind of icy clarity, something strange. He has written that we should hope, above all, that we find no evidence of life anywhere in our searches of the sky. That every time a space probe returns from a distant world, we should hope it finds nothing. That every time a telescope looks at another planet, it should see only dead chemistry. That every time a rover scrapes the soil of Mars, it should find nothing but rock. Why?
Because the discovery of life elsewhere would be, in his view, very bad news. Let us understand why. Because this argument is one of the most unsettling pieces of reasoning in modern philosophy. The great filter, remember, is the narrow passage that explains the silence of the sky. It must lie somewhere on the path from dead chemistry to galactic civilization. If we find no life elsewhere, even after careful searching, then the filter is probably early. It is probably a biogenesis, or perhaps the eukaryotic leap. In that case, we have already passed it. We are safe, relatively speaking. The road ahead may be difficult, but the deepest hazard is behind us. But if we find life elsewhere, then we know that life is not rare.
The filter cannot be a biogenesis because it happened twice or more in our own solar system. The filter must be somewhere else, somewhere later. And the later the filter lies on the path, the more of it we have yet to face. If we find simple life on Mars, we push the filter a little later. If we find complex life in the oceans of Europa, we push it later still. If we find something like a civilization, even a past one, on another world, then the filter is very late indeed. It might lie precisely in the zone we are entering now.
And the absence of living civilizations elsewhere, despite the presence of their remains, would be a grim confirmation that almost all of them fell where we are standing. This is Bostrom's argument. Every discovery of life elsewhere is a piece of evidence that the filter is ahead, not behind. Every silent dead planet we find, by contrast, is a piece of evidence that the filter was early and that we are already safely past it. Therefore, when we look at Mars, we should hope for sterility. When we peer into the clouds of Venus, we should hope for nothing but chemistry. When our probes descend into the icy crusts of Enceladus and Europa, we should hope that they return empty-handed.
We should hope, in other words, that we are alone, because the alternative is worse. It is a strange and counterintuitive argument. For generations, the discovery of life elsewhere has been imagined as the most hopeful possible finding. A vindication of our place in the cosmos. A sign that we are not alone, that the universe is friendly, that there are others like us or unlike us, but sharing the same miracle. And now, here is an argument that says the opposite. Here is an argument that says the miracle, if it is shared, may be precisely the thing that dooms us. Let us be fair to the argument. Let us also be fair to our own intuitions.
Because the argument is rigorous, but it is also cold, and there are things that rigor cannot fully capture. If we find life on Mars, yes, it pushes the filter ahead, but it also teaches us something about how common life is, and something about what life looks like, and perhaps something about how to survive. It would be, in some sense, an act of communion between worlds. We would no longer be the only example of biology. We would be one of a pair. And while the statistics would get worse, the knowledge would get better. We might learn things from another tree of life that we could never learn alone.
If we find the ruins of a past civilization on another world, then yes, we would know that the filter is real and grave and probably close to where we are. But we would also have evidence of what the failure looked like. We would have, in a sense, a case study. We could examine the ruins. We could see what they built, what they destroyed, what they failed to anticipate. We could, perhaps, learn the lesson they did not. The ruins of another world might be, in a strange way, a gift. And then there is the possibility we have not yet discussed. The possibility that the galaxy is full of civilizations, and the silence is not a silence at all, but simply the limit of our listening.
Consider, the galaxy is 100,000 light-years across. Even at the speed of light, a signal from the far side of the galaxy takes 100,000 years to reach us. We have been listening for 67 years. Anything from more than 67 light-years away that is not currently broadcasting, we cannot hear. And broadcasting is expensive. Civilizations that have been broadcasting continuously for millennia are the only ones we can easily detect. Quieter civilizations, older civilizations, civilizations that have moved to other forms of communication, are invisible to us. Our silence, then, might not be the galaxy's silence.
It might just be our deafness.
The sky might be full of conversations we cannot parse, the way a room full of people speaking languages you do not know sounds at first, like a meaningless hum. If we learn the languages, or if we build better instruments, or if we simply wait long enough, the silence may crack, and we may hear. There is a concept in science fiction, borrowed now by some serious thinkers, called the zoo hypothesis. It imagines that advanced civilizations, having reached a certain level of maturity, do not interfere with younger civilizations. They observe. They let us develop. They would consider it unethical, or simply uninteresting, to announce themselves to a species that is still figuring out its own existence.
In this picture, we are being watched, and we are being left alone, the way you might watch an anthill without disturbing it. The silence is a form of courtesy. It is impossible to prove or disprove this, but it is worth considering, because if it is true, then the silence is not our fate, but our childhood. The silence is the quiet hum of a nursery, where we grow unaware of the larger conversation until we are ready. There are other hypotheses. There is the idea that civilizations, once they mature, turn their attention inward rather than outward, that they build virtual worlds of such richness that the physical universe becomes uninteresting to them, that they upload their consciousnesses into simulated realities and stop caring about the stars.
This is a kind of inward collapse, and it predicts that civilizations, once they reach a certain technological level, simply stop expanding. They become invisible, not because they are destroyed, but because they no longer have any interest in being seen. The galaxy becomes a dark forest of civilizations curled inside their own computational gardens, tending their virtual flowers while the stars wheel unnoticed above. There is the dark forest hypothesis, proposed by the Chinese science fiction writer Liu Cixin, which offers a more chilling explanation. It suggests that civilizations are afraid of one another, that in a universe where any species might be a threat to any other, the safest strategy is silence. Any civilization that broadcasts its location invites destruction.
Therefore, all civilizations, once they are mature enough to understand this, stop broadcasting. They huddle in their solar systems, lights dimmed, signals muted, listening, never transmitting. In this picture, the galaxy is a forest full of hunters, each one trying not to be heard. There is the transcendence hypothesis, which imagines that civilizations eventually become so different from what they were that they leave behind the physical altogether. They move into some form of existence we cannot observe, some dimension of reality we cannot yet perceive. They are not absent. They are simply gone from our frequencies. And when we look for them in radio waves, we find nothing, because they have long since stopped using radio waves. All of these are possible.
None of them can be easily proved or disproved, but each one offers a different flavor of the silence. Each one casts the quiet in a different light, and together they remind us that the absence of evidence is not simple evidence of absence. It is evidence only of our own uncertainty, of the limits of what we can currently see. What we can say with some confidence is that the silence is telling us something. We do not yet know what. It might be that we are alone. It might be that we are early. It might be that we are being observed. It might be that we are one of the only survivors. It might be that others are speaking, and we are not yet listening rightly.
These are all different truths, and the universe, which is patient, has not yet told us which. In the meantime, we live. We continue. We keep listening. We keep searching. We keep building the instruments that might, one day, hear something that is not an aircraft, not a pulsar, not a glitch. We keep hoping, and we keep fearing, and we keep asking. That is what it means to be a species that has crossed into consciousness. To keep asking, and we must sit, occasionally, with Bostrom's uncomfortable wish that we find nothing, that every world we probe is empty, that we are, in this galaxy, alone. Because if we are alone, we are not because the filter is ahead of us and we have a chance.
It is a strange wish, but it is also, in its way, a form of hope. Hope that what we have become is rare enough to be safe. Hope that the struggles ahead are not insurmountable. Hope that when we look up at the sky and see no one, the reason is that the journey we have made is hard, and few are able to make it. And we, against the odds, have.
We are near the end now. We have walked a long way together. We have asked the oldest question a conscious species can ask. We have followed its branches into biology, into history, into philosophy, into the future. We have stood at the edge of our own planet's story and looked out, and we have felt as we were meant to, both the smallness of our lives and the enormousness of the silence that surrounds them. Let us, in closing, consider what this silence means, not for the calculations of astronomers, but for the quality of an individual human night.
What does it mean for you, tonight, lying in whatever bed you are lying in, to know that the galaxy may be empty or may be full, and that either way you are here, listening? It is, first of all, a loneliness, if you let it be. The sky is a vast place, and if we are alone in it, the loneliness is cosmic. There is no one out there to talk to. There is no one whose thoughts we might share. There is no one else in any direction looking back at us with eyes of their own.
The feeling of standing on a small planet orbiting an average star in an unremarkable arm of a median galaxy, and knowing that no one in any of the surrounding light years is aware of your existence, is a strange and unfamiliar feeling. It is not a feeling that any of our ancestors had. We are the first generation to know, with evidence, that the silence is real. We are the first generation to live under this sky knowingly. But the loneliness is also, if you hold it carefully, a closeness. Because if we are alone, then every other human being on this planet is not a stranger, but a companion. Every other mind in every other city is not a competitor, but a mirror.
The fact that anyone at all looks back at us is astonishing, if no one else in the galaxy does. The fact that we live among 7 billion other consciousnesses, each as mysterious and real as our own, is a miracle of local connection, thrown into sharper relief by the vast absence beyond. And there is more. there is, beneath the loneliness, a deep weight of meaning. Because if we are the only witnesses of the galaxy, then the galaxy, in some sense, exists through us. The stars that we see are stars being seen for the first time, at least in our region. The beauty that we perceive is beauty that has no other observer.
The understanding that our scientists have built, the equations, the insights, the arts, the poetry, the music, these are not things the galaxy had before we existed. They are, in a sense, our gift to the galaxy. We are the galaxy looking at itself. We are the universe waking up in a small, warm place and learning, slowly, what it is. This is the shape of the thought that, I think, deserves to be at the heart of our story. Not fear, not pride, something closer to humility and responsibility and awe, all woven together. The humility of being small, the responsibility of being, perhaps, the only ones, the awe of being here at all. Let us sit then with the silence as it actually is.
Let us not demand answers from it, because the universe does not owe us answers. Let us instead listen to it, the way one listens to an old wise friend whose silences carry their own wisdom. What is the silence telling us? It is telling us that the road is long. It is telling us that the road is narrow. It is telling us that the road is rare. And it is telling us most of all that we have, against all reasonable odds, walked some portion of it. Whatever the filters have been, we have passed them up to now. Whatever filters lie ahead, we will face them.
We are not the first species to have stood at a crossroads, and we will not be the last if we choose well. But we are in this moment at a crossroads, and the choices we make in the coming decades and centuries will determine which side of the great equation we land on, behind us or ahead. The great filter, if it lies ahead, asks us to become a kind of civilization we have never been. A civilization that holds great power without using it carelessly. A civilization that thinks in centuries, not quarterly earnings. A civilization that cares for generations unborn. A civilization that understands its own fragility and acts accordingly.
A civilization that, having learned to light the atom, also learns to sit quietly with it and not burn itself. This is not a small ask. It is, in fact, the largest ask any species has ever been asked. It is the ask of maturity on a planetary scale. And we, who are, collectively, young and impulsive and divided among ourselves, are being asked to become elders, in a hurry, without a teacher, with the tools to destroy ourselves in our hands, and only a few decades to learn to set them down. We may fail. That is the hard truth. We may join the silent civilizations, if they exist, and become one more entry in the catalog of almost made-its.
Our radio bubble may continue outward for a few more centuries after we are gone, a dying echo of our existence, before it fades into the background of the galaxy and no one, ever again, will know that we were here. But we may also succeed. That is the other truth. We may become the civilization that solves its own problems. We may build the institutions, the ethics, the technologies, the cultures that allow us to hold dangerous power without destroying ourselves. We may, over the coming millennia, become something the galaxy has not seen before. A civilization that matured,
a civilization that lasted. We do not know which future we are writing. It depends on us.
Every act of long-term thinking, every choice to cooperate, every decision to tend the commons, every refusal to use power carelessly, every investment in the future, every small act of kindness and patience and wisdom is a brick in the road ahead. The road is long, the road is not automatic, but the road is still open. And consider this in the quiet of the night. Whatever happens to us, the very fact that we have existed is a kind of victory. The fact that a species evolved on this one small planet that could look at the stars and ask where everyone else is a remarkable thing.
Whether or not we survive, whether or not we spread to other stars, whether or not we ever hear a voice from another world, we have been here. We have loved one another. We have sung songs and painted pictures and written poems. We have buried our dead and welcomed our children. We have built cathedrals and hospitals and libraries. We have cured diseases. We have walked on the moon. We have looked deep into the atom, and we have looked far into the sky. Whatever is recorded, when the galaxy's story is eventually told, our contribution to it is not nothing. It is the kind of contribution that only a species capable of wonder can make.
And so, as we come to the end of this long night, let us sit one last time with what we have. Let us sit with the silence, and let us let it be what it is. Not an accusation, not a verdict, a condition, a situation, a circumstance into which we were born, and which we are free to interpret as best we can. The silence is not against us. The silence is not for us. The silence simply is, and within it, we have our small bright moment of being aware. You are aware. You are listening right now, to this voice, in the dark of wherever you are. And in your awareness, you are participating in something extraordinary. You are the universe noticing itself.
You are a small, cooperating assembly of atoms, borrowed from stars that died long before the Earth was born, arranged into the astonishing particular shape of a conscious being. You will return these atoms in time to the soil and the air, and they will become other things. But for this little while, in this little place, they are arranged into you, and through you, the galaxy has a witness. Through you, however briefly, the silence is heard, and that is enough, perhaps, for one long night. That is enough to carry with you as you move through the days ahead, whatever they bring. That we are here, that we are aware, that we are, each of us, a small lit lamp in a large unlit room.
That the lamps are precious, that the lamps are rare, that whether or not any other lamps exist, ours burn. Let them burn gently, let them burn carefully, let them burn for as long as they can. That is the only advice the great filter can really give us. That is the only wisdom the silence can really share. Before we close, let us return once more to Fermi, on that summer afternoon in 1950. He did not think of himself as asking one of the deepest questions of his century. He thought of himself as making an offhand remark. He died in 1954, 4 years after that lunch, at the age of 53.
He did not live to see Drake's first experiment, or the Apollo missions, or the discovery of exoplanets, or the silence of 67 years of SETI. He left the question in the air, and the air has held it ever since. What has changed
is that we now understand how deep the silence is. We know how many stars there are. We know how many planets. We know that the ingredients of life are everywhere. We know that self-replicating probes could have filled the galaxy 1,000 times over. The silence is not just an absence. It is a structure. It is telling us something. And we know one more thing Fermi did not. We know about the Great Filter.
The idea, as a formal concept, was articulated by Robin Hansen in 1998. He gave it a name, and in giving it a name, he made it a thing we could reason with. We live in the first generation that has the conceptual vocabulary to think clearly about our own potential extinction. We are the first generation of our species with the tools to destroy itself. We are also the first generation with the tools to recognize precisely the nature of that danger. Both tools arrived in the same century. We were given the gun and the warning together. Whether we heed the warning is our choice. The silence, if it is telling us anything, is telling us that many before us did not.
But we are not bound by the usual outcome. We are not a statistical law. We are a particular civilization on a particular planet at a particular moment. Our own fate is ours to write. There is a prayer that seems right for this moment. It is not a prayer from any tradition. It goes, "Let us be wise. Let us be kind. Let us last." Wisdom, kindness, duration. Intelligence is the easy part. Wisdom is harder. Kindness is harder still. Duration, the patient willingness to last, is hardest of all. But it is what the stars, in their quiet turning, are asking of us. When you go out tonight, and you look up at the stars, listen, not with your ears.
With the part of you that can hold enormous questions in a small space, the silence is not empty. The silence is full of the unmet, the unborn, the paths not taken, the civilizations that might have been and were not. Full, perhaps, of the children we have not yet had, who will, if we are careful, inherit this planet and learn, in their turn, what the silence means. The sky is a library. Every star is a volume. Most are closed. We have opened a few. We have listened for the voices of their authors, and the voices have not come, but the library is open. We can keep listening. That is what we have become, a species that listens.
Fermi's question, "Where is everybody?" may never be answered in the form he imagined. But in the end, the question may not be about them at all. It may be about us. It may be asking whether we, small as we are, will be among those who, when asked, can finally answer. Here we are. We made it through. We are here. Close your eyes now, if you are able. Let the long weight of the galaxy fall away. Let the silence that has held you through this night soften into the silence of your own breath. The stars will keep turning. The filter, wherever it is, will remain the filter.
And you, for this little while, can simply be here, on this small, warm planet, part of the one civilization that we know, for certain, exists. Rest now. Rest deeply. The galaxy has waited 10 billion years for you to become aware. It can wait a little longer while you sleep. In the morning, the sky will still be there, and the questions will still be there. For now, the silence is yours. It holds you gently, the way the dark holds the stars,
the way the universe holds the small living thing that is you. Sleep well. The silence is with us. And for this one night at least, the silence is enough. Total: 17,500 words, 12 chapters. 12 Talks Brak 1.